This video is going to explain the very beginnings of species in solution. It's going to be a series of videos. So we're going to be looking at a range of substances. We're going to look at non-electrolytes, what ions or species you get when those are put into water. The next lot that we'll look at will be the strong acids and strong bases and the species that those ones produce, followed by weak acids, weak bases, and then we'll get into the salts. This will become clearer once you've gone through a few more videos. Now, because we're looking at aqueous solutions, there is always going to be the presence of water. And water self-ionizes. In order for it to do that, you need two water molecules, and one of the water molecules will lose its hydrogen atom, and it will be gained by the other water molecule. And so what that does is it produces the hydronium ion, which is what's represented here, and a hydroxide ion. And those will be in equal concentrations. Now there is this value, the ionic product of water. It's a constant value at 25 degrees Celsius. And we can use that as well as the knowledge that they produce hydronium and hydroxides in equal quantities, and we can work out the concentration of the hydroniums in a water solution, and that's 1 times 10 to the minus 7. Now that is a very small concentration, and the concentration of the hydroxides in a water solution will also be 1 times 10 to the minus 7. Now, as we progress through and look at the various aqueous solutions in the standard, you're going to find that water is in all of them because these are aqueous solutions, which is why they're called aqueous solutions, because there's lots of water. Now, we might get asked to show our species present in a graphical form, and that's what this shows you here. Now, I'll explain where this 55.6 comes from. Now, it will be on every graphical representation because every species we look at will be dissolved in water. So what we do is we consider 1 litre of water, because all our solutions are moles per litre, and we use the density of water and convert our 1 litre into mass, which is the equivalent of 1,000 grams. Now we know the molar mass of water, and you can calculate that if you want to. The mass of your 2 hydrogens and your oxygen, add them together, and that's where this 18 grams per mole comes from. So that's the molar mass of water. So to find the amount of water molecules in a litre, you take your 1,000 grams, which is your litre of water, you divide it by your molar mass, and that's where you get your 55.6 moles. So every litre of water contains 55.6 moles. Now, you're going to be looking at a few of these graphical representations over the next few videos. You're now going to understand why it is that water is always the first bar on the bar graph, and why it's 55.6 here, although it's not required for you to write 55.6 if you're asked to draw the graph. And this here represents it's broken. The reason being is it's very difficult to graph this. This vertical y-axis is to represent the concentration. These values are incredibly small. That's the concentration of the hydroniums and hydroxides, whereas this concentration is incredibly high. So this just represents that it's a broken bar and would go up to 55.6, which would be incredibly tall. The takeaway important point to note here is that yes, you've got hydroniums and hydroxides. They will always be present. You'll always get these 3 bars on your graph. So water will always be furthest to the left and the tallest and broken because it's such a high concentration. and your hydronium and your hydroxides will always be present, and they will typically, in 90% of cases, be on the right hand side because their concentrations are the smallest. Whenever you see the bars equal height for the hydroniums and hydroxides, that's an indicator that you've got a neutral solution, okay, that the pH is 7. So I'll stop this video here to keep it short, and in the next video I'll explain to you molecular compounds.